In this video, we're going to continue looking at the quotient ring Z mod in Z. From the last video, what we know is that this set Z mod in Z is nothing more than the left cosets of the subring in Z inside the ring Z. And we defined an addition that looks like this. We defined the sum of the left coset A plus in Z and the coset B plus in Z to simply be A plus B plus in Z. In other words, to add two cosets together, we're going to add their representatives. Likewise, we defined a multiplication on our set of left cosets, where we wound up doing nothing more than to multiply two left cosets. We're simply going to multiply the two representatives together. At the end of the last video, I posed the question, are these two operations well defined? Well, the very first thing that I want to look at is that particular question. When I ask the question whether or not the two operations are well defined, what I really mean is this. If we take two names for the same coset, in other words, A1 plus NZ and A2 plus NZ are the same coset, and B1 plus NZ and B2 plus NZ are the same coset, but they're different names. The question is whether or not, when we add the two things, do we get the same answer? And when we multiply the two cosets, do we get the same answer? And so that's what we're going to be investigating in this particular video. So let's see, how are we going to investigate whether or not the addition is well defined? Well, we start with the idea that A1 plus NZ is equal to A2 plus NZ, and B1 plus NZ is equal to B2 plus NZ. And then, of course, the question is, what does that tell us? Well, this particular thing is going to tell me that A1 minus A2 belongs to NZ. In other words, A1 minus A2 is equal to N times Q1 for some Q1 inside the set of integers. And likewise, knowing that the two B cosets are equal says that B1 minus B2 is inside N times Z, and that's going to tell me that B1 minus B2 is equal to N times Q2 for some Q2 inside Z. And I want to use these facts to show that it doesn't matter which way I add the two cosets together. So in other words, what I'm now going to look at is this idea. Let's compute A1 plus NZ plus B1 plus NZ. And when we do, we're going to get A1 plus B1 plus NZ. And when we compute A2 plus NZ plus B2 plus NZ, we're going to have A2 plus B2 plus NZ. And our whole question is, are these two cosets equal? Well, to figure out that, what I want to do is I want to look at their representatives, and I'm going to take this representative and I'm going to subtract off that representative. In other words, to tell whether or not the two cosets are equal, we're going to look at this particular computation. A1 plus B1 minus A2 plus B2 is going to be A1 plus B1 minus A2 minus B2, and that is an equation inside the ring Z. But we can keep going. Because we're in Z, we know that addition is both commutative and associative, so I can rewrite that sum as this. Parenthesis A1 minus A2 plus parenthesis B1 minus B2. And I want to recall some facts from above. We're going to go back and look at them, and then I'm going to write them down. we've already said A1 minus A2 is equal to n times Q1, and B1 minus B2 is equal to n times Q2. So I want to copy these two facts down where I'm doing my work. A1 minus A2 is equal to n times Q1, and B1 minus B2 is equal to n times Q2. And using those facts, we can then say that what we've got is n times Q1 plus n times Q2, which is, of course, n times Q1 plus Q2. And that is a multiple of n, so it belongs to n times z. In other words, what we have now is that A1 plus B1 minus A2 plus B2 does belong to the subring n times z, and hence A1 plus B1 plus nz is indeed the same left coset as A2 plus B2 plus nz, and that says our addition is well defined on z mod nz, the set of left cosets of z. Well, now that we know that addition is well defined, the question, of course, is, can we do the same kind of thing with multiplication? Now, I would encourage you to stop the video and try to do the proof by yourself. And after struggling with that for several minutes, then come back and start the video again and compare your work to the work that I do. Hopefully you did that. Well, how are we going to look at whether or not multiplication is well defined? We start off with the same set of ideas. We're going to let our first coset have the names A1 plus nz and A2 plus nz, and the second coset is going to be named both B1 plus nz and B2 plus nz. And of course, the question is going to be, is this product here the same as this product? And again, what we're going to do is we're simply going to compute things. Now, A1 plus nz times B1 plus nz was defined to be A1 B1 plus nz. And A2 plus nz times B2 plus nz was defined to be A2 B2 plus nz. And these two things are going to be equal if and only if the subtraction of this representative minus that representative belongs to the subring. So what we want to do is we want to figure out whether or not these things are equal by looking at, is A1 B1 minus A2 B2 inside n times z. If the answer is yes, then these two sets are equal. Now, I do want to recall that we've already seen that A1 plus nz equals A2 plus nz implies that A1 minus A2 is equal to n times Q1, and B1 plus nz equals B2 plus nz is going to imply that B1 minus B2 is equal to n times Q2. So what we now know is we can use these facts when we're looking at this particular statement. So let's look at this. I'm going to look at A1 B1 minus A2 B2. And because I don't know anything else about what to do, I'm going to add and subtract the same thing. I'm going to first of all subtract off, let's make it A1 times B2, but if I subtract that off, I'm going to have to add it right back. And that should have a 2 there. So, and all I've done here inside this set of parentheses, this guy is a big fat 0. So we haven't changed the expression at all. But what I have done is I've given myself the ability to factor some stuff out. I'm first of all going to reassociate in this fashion. And you'll notice that from the first two terms, we can factor out an A1. And from the last two terms, we can factor out a B2. Now recall these two facts. This fact here and this fact here both get substituted in the expression that we're looking at. This mess here is n times Q2, and this mess is n times Q1. So our next step winds up simplifying things down to A1 times n times Q2 plus n times Q1 times B2. And because we are inside the integers, addition and multiplication are both commutative and associative, and so we can factor the n out, and we are left with A1 times Q2 plus Q1 times B2, and that is clearly an element inside in Z. So what we've actually done when we look at this is we've shown that this guy here belongs to n times Z. So A1B1 minus A2B2 belongs to my subring n times Z, and what that says is A times B1 plus NZ will indeed be A2 times B2 plus NZ, and that means our multiplication is well defined. In the next video, we will look at whether or not we have a full-fledged ring in this quotient structure.